Okay, in this lecture we're going to finish our section 2.1 material on vectors in the plane. So in this lecture we're going to talk about some applications of vectors to physics and engineering. And we'll start by considering applications which involve finding a net force or a resultant force acting on an object. So recall that a vector is some quantity that has both magnitude and direction. So we can use vectors to represent forces, or forces can be considered as vectors. So we'll say the following. A force is represented by a vector since a force has both a magnitude, which is typically measured in pounds or newtons, and it has a direction in which a force is acting. So let's consider the problem that we have several forces acting on an object at any time. And the question is, well, what is the resultant force experienced by that object? And it's defined to be the sum of all of the forces acting on our object. So if we have, for instance, let's say some ball, and there's several different forces which are pulling or pushing on this ball at a given time, the question is, well, in what direction will that ball move? So we need to determine what the sum of all those forces would be to determine the magnitude and direction of motion of that ball. And we'll see some examples involving not just forces, but velocities as well. So as a simple example of this type of problem, let's consider the following. We have two forces, F1 and F2, so these are vectors, F1 and F2, which have magnitudes 10 pounds and 12 pounds. And these are acting on an object at some point P, as shown in our figure below. So here we have a point P. We can think about this point as maybe being the origin of the XY plane. And we see that there's two forces acting on this. The first force, F1, we're told has magnitude 10 pounds, and we can see that it forms an angle of 45 degrees upward from the horizontal. And we have a force F2, which is also acting on that object. We're told that force has a magnitude of 12 pounds, and we can see that it forms an angle of 30 degrees measured from the horizontal. So the question is to find the resultant force F acting on this object P, as well as its magnitude and direction. So if we sum those two forces, F1 and F2, we will have a resultant force, which we're calling just F, and we want the components of that force along with its magnitude, or the length of this arrow, and its direction, which will be indicated by the angle measure theta from the horizontal. So let's think about how to find this. To find the resultant force acting on an object, it's the sum of all forces acting on the object. In this case, we only have two forces acting on our object, F1 and F2, so we need to find the components of those two forces. And what we're given is information about the magnitude of F1 and F2, and the angle that they form from the horizontal. So we can use what we had talked about in the first part of this section in terms of finding the components of a vector from its polar coordinates, and recall that the formula we could use would be the following. F1 would have an x component given by r cosine theta, where r is the magnitude of this first force, F1, which we were told is 10 pounds. And then we're multiplying by cosine of theta, where theta can either be considered as the angle that we rotate counterclockwise from the positive x-axis by, Or in this example, we were given the angle measure from the horizontal was 45 degrees. And since this vector is pointing towards the left from the origin, our point P, its x component would be negative. So I could calculate this as negative 10 times cosine of 45 degrees. And my y component would be the magnitude r times sine of 45 degrees. And since this vector is pointing upward from the origin, the y component would be positive. Or an alternative approach here would be to take 10 times cosine of the angle that's formed by rotating from the positive x-axis to this vector, which would be 180 degrees minus 45. So that would give us 135 degrees, and 10 times sine of 135 degrees. So either approach you use, you have for your first component 10 times cosine of 135 degrees or negative cosine of 45 degrees gives us negative root 2 over 2. And our y component, either 10 times sine of 45 degrees or 10 times sine of 135 degrees, gives us 10 times root 2 over 2. So we're left with our components for the first force, F1, as being negative 5 root 2 and positive 5 root 2. Now the next thing we need to find is the components of the force F2. Now we're told that the magnitude of that force, which we would call R, is 12 pounds, and it's acting at in a direction which is determined by rotating 30 degrees counterclockwise from the horizontal. So using what we know about polar coordinates, we would take the magnitude of that vector, which was 12, times cosine of the angle, which is 30 degrees, and 12 times sine of that angle, 30 degrees, formed from the horizontal. So we have then 12 times cosine of 30 degrees, which is root 3 over 2, and 12 times sine of 30 degrees, which would be 1/2. So this leaves us 6 root 3 and 6 for the components of F1 and F2. So to find the resultant force acting on our object at point P, we take the sum of these two forces, F1 and F2. So to add these two vectors, we would add their components. So the x component is going to be negative 5 root 2 plus 6 root 3. And the y component is 5 root 2 plus 6. So this would be the resultant force that we were interested in. Now we were also told in the problem to find its magnitude and its direction. So to get the magnitude of this resultant force F, well, remember the magnitude of a vector is defined as the square root of the sum of the squares of its components. So for our first component, we had negative 5 root 2 plus 6 root 3 squared. Plus, for our second component, we have 5 root 2 plus 6 squared. We're taking the square root of that value. So by making use of a calculator or some software, we find that the magnitude of this resultant force F is approximately 13.5 pounds. Now, the last part of this question asks about the direction in which this resultant force is acting. And as indicated in the figure, we're supposed to indicate direction by finding the angle theta that's formed from the positive x-axis, rotating counterclockwise to get to that resultant force F. So how are we going to find that angle measure theta? Well, we have the components of this resultant force. So those are the coordinates for the terminal point of this resultant vector F, which we would call maybe x and y. And we know that in terms of polar coordinates, tangent of an angle theta measured in polar coordinates would be given by the ratio of y over x, where x and y are the Cartesian coordinates for our point. So to find our angle measure here, we can say, well, tangent of this angle measure theta would be given by the ratio of y over x. Now the y component for our vector F was 5 root 2 plus 6, and then we're dividing by the x component, which was negative 5 root 2 plus 6 root 3. So to get the angle measure theta, well, we could take theta as arctangent of this angle measure, 5 root 2 plus 6 over negative 5 root 2 plus 6 root 3. And the value that we would find here is measured in radians, remember. Now, typically for problems in physics and engineering, we might not give this angle measure in terms of radians. We might prefer to give it in degrees so that it's a little more a familiar number to work with. So remember our conversion from radians to degrees. Well, if we have our angle measure in radians, which would be arctangent of this quotient, 5 root 2 plus 6 over negative 5 root 2 plus 6 root 3, we would then multiply by the ratio of degrees to radians. Now 180 degrees is the same as pi radians. So we're taking this angle measure, arctangent of a ratio, which was in radians, multiplying by this ratio to convert to degrees, and we have an approximate value of 76 degrees. So that would be the angle that we rotate by counterclockwise from the positive x-axis to indicate the direction in which that resultant force is acting. Okay. So let's look at another one, sort of a similar problem, but maybe a little more complicated. So here we are told to suppose that a wind is blowing from the direction 45 degrees west of north with a speed of 50 kilometers per hour, and a pilot is steering a plane in the direction 60 degrees east of north at an airspeed, which is speed in still air, of 250 kilometers per hour. And we're asked to find the true course, that is the direction of the resultant vector, and the ground speed, which would be the magnitude of the resultant vector of that plane. So if we know the velocity, the wind velocity and the direction that it's blowing from, And we know the direction in which our pilot is steering, along with his airspeed, which is the speed in still air without any wind speed. Then we can determine the true course of the plane and its ground speed. So let's think about how to do this. It's going to help to visualize our problem. So here we have a set of axes which we're going to use to define direction. So I will label the positive y-axis due north, the negative y-axis south, the negative x-axis as west, and the positive x-axis as east. So let's look at the information that we're given here. So we are told that we have a wind which is blowing from the direction 45 degrees west of north. So let me talk about this notation a little bit. This notation where we have north 45 degrees west means that from the due north direction, we are going to rotate 45 degrees in the western direction. Now, we've got to be a little bit careful with our wording here. We're told that the wind is blowing from that direction. So we're not moving from the origin outward in that direction, but the wind is coming from that direction. So let's say that we're placing our, figure out what I want to use here. Let's say that our plane is going to be considered at the origin. So we have this wind blowing from this direction towards our plane. So another representation of this wind velocity vector would be to take its position vector. So that is the vector whose initial point is at the origin, and it's acting here. Well, we would have this complementary angle of 45 degrees downward from our positive x-axis. So this is our vector representation of the wind velocity acting on our plane. So I'm going to call this, let's call it V1, which will be my wind velocity. And it's acting at a speed of 50 kilometers per hour. So that's the magnitude of that velocity vector. Now we're also told that we have a pilot which is steering the plane in a direction 60 degrees east of north. So again, this notation, north 60 degrees east, means that from the due north direction, or the positive y-axis, I'm rotating towards the east by 60 degrees. So the pilot is steering the plane in that direction. So that would mean that from the positive x-axis, we were rotating 30 degrees counterclockwise. And we were told that the airspeed, so the speed with no wind resistance, would be 250 kilometers per hour. So that will be the magnitude of the velocity vector for the plane. I'm going to call that velocity vector V2. So then the question is, well, if both of those vectors, wind and the velocity vector being imparted by the plane, are acting on the plane at this point at the origin, what is our net resultant force? So we're moving in some direction, which would be called the true course of the plane. I'm going to call that vector V. And we need the magnitude and direction of that vector. So let's see if we can find it. The first thing that we need to find are the components of the vectors V1 and V2. So here let's start with our wind velocity vector. So here I'll say a vector for the wind velocity would be found by V1. And to get V1, let's think about how to do it. So we saw in our sketch here that the vector V1 formed an angle of 45 degrees from the horizontal, and our vector is pointing into quadrant 4, which means that the x component is positive, the y component is negative. So using what we know about polar coordinates, well, the magnitude of this vector, which is the wind speed, was 50 kilometers per hour. And to get our x coordinate, we would take cosine of that angle measure, 45 degrees. Now to get our y coordinate, we would take the wind speed, 50, which is the magnitude of our velocity vector v1, times sine of the angle 45 degrees. But since this vector lies in quadrant 4, that means that this y component is negative. Now, alternatively, you could think about what would be the corresponding angle measure that you would have to rotate counterclockwise by to get this vector. And you could use cosine and sine of that angle, and you'll end up with the same expression for these components. So let's see what we have here. For our first component, we have 50 times cosine of 45 degrees, which would be root 2 over 2. And then a negative 50 times sine of 45 degrees, which is root 2 over 2. So V1 is given by 25 root 2, negative 25 root 2. So now we need to find a velocity vector for the plane. So a vector for the plane, or the plane's velocity, is given by what we were calling V2. And here we saw that the vector V2 formed an angle of 30 degrees measured counterclockwise from the positive x-axis. And the airspeed of this plane was 250 kilometers per hour. So we would have our magnitude of that velocity vector, which is 250. And for the x-coordinate, we would multiply by cosine of the angle 30 degrees. And 250 for the y-coordinate sine of 30 degrees. So this gives us 250 times cosine of 30 degrees is root 3 over 2. And 250 times sine of 30 degrees is 1/2. So we're left with a vector 125 root 3 and 125. So the resultant velocity then would be given by what I was calling V, and it's the sum of the wind velocity and the plane's velocity. So let's see what we have. Adding the components of these two vectors, I have 25 root 2 plus 125 root 3 and a negative 25 root 2 plus 125. Now, the problem asks us to find the true course, which is the direction of this resultant vector, and the ground speed, or the magnitude of the resultant vector for the plane. So let's start by finding the magnitude. I think that's a little bit easier. So here, the ground speed is the magnitude of this resultant vector v, which is found by taking the square root of the sum of the squares of the components of that vector. So we had 25 root 2 plus 125 root 3 squared, and then plus a negative 25 root 2 plus 125 squared, and we're taking the square root of that quantity. So again, using a calculator or some software, we can find that this ground speed is approximately 242 kilometers per hour. And we need to determine what the true course is. So we're curious, well, from the positive x-axis, what is this angle measure that we rotate by to get to the resultant vector v? And again, we can find that by using our conversion formulas for polar coordinates. So we know, in particular, that tangent of theta, where theta is that angle measure that we're interested in, is given by the ratio of y over x, where the y component of our velocity vector was negative 25 root 2 plus 125 over the x component, which was 25 root 2 plus 125 root 3. So to get the angle measure of interest, theta, we would take the arctangent of this ratio, negative 25 root 2 plus 125 over 25 root 2 plus 125 root 3. And this value, if evaluated on a calculator, would give me an angle measured in radians. But since in the problem all of our angle measurements were given in degrees, we might want to convert back to degrees, which we could do by multiplying by the ratio. 180 degrees is the same as pi radians. So evaluating this expression using a calculator or software, we get theta is approximately 20 degrees. So one way that we might want to give our answer here is in the same sort of notation that was used in the problem. So we have here 20 degrees is the angle measured from the positive x-axis in the counterclockwise direction to get to our resultant vector v. But in the problem, everything was measured in terms of an eastern or western degree rotation from the northern direction. So if we're rotating 20 degrees counterclockwise from the positive x-axis, that would correspond to an angle measure of 70 degrees downward from the due north direction. So here we could say that the true course is approximately from the northern direction 70 degrees towards the east.